Hi everyone. Welcome to module number 2, and practical training on the concepts of machine learning and deep learning that we reviewed together in module number 1. I see that lots of people are still joining, so I will start and hopefully others will catch with us soon. So please remember that this webinar is being recorded and the recording will be publicly made available after the session. And I wanted to make another reminder about our next session, module number 3, which is going to be really on applications of machine learning and deep learning on oh, sorry, I think I put the wrong one, but the QR code will be good. I still put the date for today's or okay, no, you can see, sorry. My mistake. I just removed the English versions actually. So this is our session 2 and our session 3, which will be really on the applications of geospatial artificial intelligence, specifically on image data, raster data basically. So please, if you haven't already done so, feel free to use this QR code and register to attend our 3rd session as well. And then, like last time, we do have a Google Classroom through which you will have direct access to the material of this session, the past one, and the next one as well. Please just note that for joining the classroom, you will need a Google account, and when joined, the other classmates will be able to see your name under the People tab of the classroom. It won't show your email addresses or other information, just your name as is associated with your Google account. So on top, there is the QR code to join us on the Google Classroom. And on the bottom, we have our GitHub repository where you can find a copy of the material through the repository as well. So I can give a few minutes if you wanted to scan or access any of these links. So just before starting, I would like to also begin by acknowledging that I'm working at and joining this webinar from City of Sherbrooke in province of Quebec in Canada, which is located on the traditional ancestral territory of the Abenaki people and the Wabanaki Confederacy. I want to express my respect and my gratitude to these communities who have stewarded this land since time immemorial. Perfect. And for those of you who weren't with us in the first session, my name is Mojde. I'm a scientist at Natural Resources Canada at a branch called Canada Centre for Mapping and Earth Observation, CCMEO. My main areas of expertise are photogrammetry, computer vision, and geospatial artificial intelligence. I'm very glad to be here with you and ready to start our second module. So I thought it would be good to bring everyone up to speed about programming aspects because this session and the next one will have a lot of programming involved. I will do the heavy lifting and I will explain for those who want to follow me live in the code how they can do that, and those who prefer to follow the videos later at home on their own local machines, how they can do that as well. So I just prepared a few slides to talk about what programming is, specifically when it comes to programming in Python language, which is the language I will be using both in this module and next module for training purposes. And it's also a language of preference for a lot of geospatial AI developments. Lots of helpful libraries and packages already exist, developed by others. There's a very strong, good open source and open access community around programming with Python, which makes it very suitable for geospatial artificial intelligence uh, practical applications, basically. So programming is basically just designing a sequence of instructions for solving a problem. And that's something that we do regularly as humans. When it comes to programming, the difference is that now we have to make those instructions readable and understandable by a compiler. And a compiler is basically just a computer software that will translate human readable instructions into machine readable instructions into zeros and one, basically. So these instructions will be written by us as what we know source codes. So these codes, they follow some rules, some syntaxes that are set by any programming language in which we are writing our source codes. So every programming language like Python, C++, Java, they all have their own sets of rules and syntaxes to follow when you're writing source code. So source code is, when we are speaking of source code, is just a set of instructions set by us following the rules and syntaxes of our programming language in order to instruct the machine to do something for us. So it's sort of a cycle as well. So you would always, just like as humans we always do, we think about the solution to our problem, and we would design detailed instructions to solve that problem, and then we will translate from our human language to a Python program language those instructions. And that would become our program, our source code that we would run. Usually at the first try, we don't get it right. There will be bugs and issues that needs to be fixed. And then we repeat the whole chain, the whole cycle basically again. So we usually divide our problem to smaller pieces, as I will show you today. We'll try to solve one piece, remove its bugs, fix it, have the results from that piece, and then design the next piece of the code and so on. So usually there might be some programs that have many source code files, thousands of source code lines in it, but they are not all written at the same time. They are written in pieces. So here is a very basic sample source code in Python language. So in Python, all the packages that you need to refer to, you get them through a command called import. Some packages are default Python packages, so whenever you install Python, they will be installed with it. Some packages are more specialized. They will not come with the default Python package, so you would have to install them separately. We will talk about that during this tutorial as well. And then usually in the source code, you have a series of functions. We will talk about that a little bit more. And then there is a main part of your source code that indicates which functions with which kinds of inputs should be running, what kind of output we should get out of that, and so on. So, as we said, let's break it down and see how we should think to be able to write a good code. So we have to organize our thoughts a little bit more systematically than we usually do as humans to be able to convert or translate those thoughts into instructions for a machine. So let's say I have a problem, I have a point and a plane, and the question somebody's asking me is to confirm with them whether this point is lying on that plane. So whether point A is on plane P. So my solution would be, again, in terms of really simplified and um, categorized type of instructions. So first of all, I need the user to give me their coordinates of the point A. So I have to take that in. So that's already taking something from a user is a type of instruction that we can translate to a machine. And what I need are the coordinates, or the 3D coordinates of that point. And then if you're talking about a plane, plane is representable by a set of 4 parameters. So I need the user also to give me those. So the machine should take in the parameters of the plane. And then I have to calculate, so it's an action, it can be a function, for example, to do that, the distance of the point from plane. And if that distance is 0, then I would say the point is lying on this plane. And I have to return the answer to the user. And otherwise, so there is a if and otherwise or if and else structure that I put in for decision making. So otherwise, the point is outside the plane, and my answer to the user is no, the point is not lying on the plane. So this is something like this, specifically nowadays with AI agents. If I break down my thoughts or my solution to something even simpler than this, um, by starting by with a base like this, and I give this to any AI agent, they usually will do a good job of translating these sets of instructions or this kind of pseudocode basically into an actual source code in the language of preference, and all I have to do next is just to test it, debug it, and make sure it's working, then move on to the next set of instructions. So that's why again, nowadays, specifically with the help that we can get from AI agents, these kinds of simplified instructions, but clear and comprehensive ones that we can also refer to as prompt, they can be very helpful to get help from an AI agent or for ourselves if we are coding from scratch. So when we are working in a source code, we have to define things, right? So here, for example, I'm saying take these coordinates, those parameters, calculate a distance. So I need some container basically to store the values of these kinds of variables. So exactly they are variables. And we have to store our data, we need these variables, and we have different types of variables. So variables can be numeric, they can be integers, floats, or even complex with imaginary parts. They can be Boolean, true or false. They can be sets in Python to show a sets of items or a sets of other variables. Like here, my set includes 2 numeric variables and 1 string. Uh, and in Python, there is no distinction between a string of more than one character or just one character, like in this case. And a set has this property that it doesn't hold repetitive items. So if I add another one into this set, it's just going to ignore it because item 1 or variable with value 1 already existed in this set. That's a very particular behavior of sets in Python. And to define a variable as a set, we have to use these purchase. And here we have another type of variable, which is a dictionary. A dictionary is made of two parts. Each item in the dictionary is made of a key, and that key can have a value. Again, the key can be a numeric or a string type of variable, and the value can be anything. Can be numeric, can be anything else. And you can have as many items as you want with whatever diversity in terms of type of the key and the type of the values that you want in your dictionary. The only thing that can now happen in a dictionary is to have repetitive keys. So now here I have a key that is called name, and that key has a value called Mojde. And then I have another key that is called age, and that key has a value of 20. Here I have a key that is number 2, and that key has a value letter C. So I cannot have, for example, another item in this dictionary with exactly the same thing, the same key as name. If I want to add more values to this name, I could change this to a sequence, which is a different type of variable that can hold, for example, a list of items. So here, and we use this uh, not curly brackets, the square brackets to hold the items of a list, so or elements of a list. So here I have this element, which is just a numeric value, this element, which is a string, this is a float value, this is an integer value. I could have a dictionary within the list and so on. And then a counterpart to list is tuple, which is exactly the same as a list, but they are not mutable. It means you cannot just decide to change this value that is part of this tuple, and it's creating some sort of safety or security from other developers and other parts of the program on this specific variable. Whatever it is inside it, it will stay as it is. And then strings are known as sequences too because they are basically a sequence of characters. Again, a string in Python can be either shown by a double quotation or a single quotation, and doesn't matter if it has one letter like here or it has several letters. So these are the basic types of variables, or basically different types of data that can be stored into Python variables. So let's see a few examples. So this is how you would define a variable. Here I have a variable A. Oops, sorry. I have a variable A, and let me open. I have a variable A, and I'm assigning value 100 to it using the assignment operation. I have a value, I have variable named B, and I'm assigning a float value of 2.5 using the assigning operation. Same thing, I could explicitly say that this is string of 3.44, convert it to a float number, and then assign it to variable D. Same thing here, this is string, a value of that looks like string 10, convert it to an integer, so it will become a number 10, and then assign it to variable A. Booleans are just false or trues. Sets, again, with these curly brackets, we define them, and they can contain any other type of variable. The only thing is that they can now have repetitive items in them, and we can always get their length. It means the number of variables that they are holding as with the function len. So for all types of sequences, this function len would work. A dictionary, so we have keys and values. So here we have the key myset, and the value is a set as a variable, and so on. And we can get all of these values like set12 string Mojde string hello using calling the function values on our variable. So when you use a data operation, it's like calling this over your a variable. It means show me the values that are held within dictionary A. And this is showing the keys that are held within dictionary A. And here I'm referring to a specific key. So this key of dictionary A, and the output will be the value of that key. So when I call a key on my specific key with its full name on my dictionary, it's going to return me the value. Strings, as I said, they can be sentences, words, characters, they are all strings. Lists, they can hold different types of items. You would be able to access the items within the list using their index. And in Python, indexing starts from 0. So this number 1 is at index 0 of list A. Number 10 is the item located at index 1 of list A. This string 8232 is located at index 2 of list A, and so on. So when I say get the item of index 2 of list A and then assign it to variable C, it means 0, 1, 2. The variable C will become equal to this string. We can also do a backward type of indexing. So the last item of a list gets an index -1. So index -1 of A is referring to this element, which is number 1, and then I'm assigning it to D. We could also slice a list over several indices. So here I'm slicing A from index 1 up to but not including index 3. So the output will be A at index 1 and index 2 only. So the output of this will be, well, I'm just printing it, but if I was assigning it to another variable, it would have been another list of 2 items, the 10 and the string 8232. Lists are mutable, so I can get an item of the list and change it. So I can get item 0 of the list and change it to a string variable. So now if I print my, if I look at my variable A, it will not be 110 something else. It would be hey 10 82321 because I changed its number 1. We can add items on top of our list at the back of our list. So when I say append something to my list, so append number minus 10.5 to list, so it will become or we change it to hey, so it's hey 10 82321 and then minus 10.5. We could extend several elements to our list. So it's like repetitively appending items. So it's first appending this and then appending this item on top of our existing A. We could append it with another list. So here I'm appending my current list with a list of 2 characters. So my list will become a whole list of these items and another list. So a list can hold in another list as one of its items. Tuples are very much similar to lists. The only thing is that they are not mutable. It means if I try to change the value of certain index, here I'm trying to change the value of whatever variable that is located at index 0, this won't be allowed. So there is no kind of direct assignment or direct change that is possible to our tuple. So as a quick exercise, why don't we all take just a few seconds and let's see what will be shown or printed if, for example, I would have printed all of this. What would have happened at all of these commands? So the value of C would be A232 as a string. The value of D, it's the last item, so that would be 1. When I print something as a slice, so slice from item 1 up to, not including item 3. So 1 and 2, so that will be another list of 10 and A232. This, I'm making a change to my list, so it's basically replacing this one with a string. Here I'm appending a value, so it's basically as if I continue this. So it's a comma and minus 10.5. And then here I'm extending 2 more values on top, so that would be 1001 and then 1021. And then here I'm appending a whole list, so it will be a list within a list. So that would be list BC. And now this is the last change I made to my list. So the whole up to here, we changed this whole A into looking like this. So we already saw a few operators, the assignment operator, which assigns a value to a variable. We have the arithmetic operators that can apply on numeric values. So we have the plus minus multiplication division. We have the modulo. We have the integer or floating type of division, and we have power. We have some combined assignments that would allow us to shorten our instructions. For example, if I say A plus equal 1, it means the same thing as A equals A plus 1. So it's just a compound and shorter version of the same thing. And then we have comparison operators. Basically, they would be like for comparing a variable to another. For example, is variable A equal to? Is variable A different from? Is variable A larger than variable B, smaller than, larger or equal, smaller or equal? And then we have logical operators that are applied on binary decisions. So, for example, a binary 1 and a binary 0, or a true and a false will give us a false result. So and means if both things are true, the result will be true, otherwise the result will be false. Or is if at least one of the results is true, one of the comparables are true, then the result will be true, and so on. And we have to be sure that when we are using these operators, there is a precedence defined in any programming language. So if you have multiplication, division, or modulo operations, they precede your plus minus. So if I write 3 multiplied to 6 plus 2, the program will first do this operation and will get the result and then add it to that. So the result will be 20. And after arithmetic operations, comparison operations, and after that, even within the relational operation, we have relational operations. We first have precedence on inequality, and then we have on equality, and after that we have our logical operators, and at the end the assignment happens. So if I have A equals, let's see, 4 divided by 2 plus 2 equals 5. So what will happen? First, this will take place. This will give us 2. Then this will take place. The result will be 4. And the next thing is gonna ask this question, is 4 equal to 5? The result is no, false. So what we will return to A, or what we will assign to A, is false. So A becomes a Boolean operator, a Boolean variable containing value false. So there are some control structures to make either decision making possible, or to be able to iterate over certain instructions. And they are known as conditional branching or iteration structures. So conditional branching, it's basically like when you want to make a decision, if this happens, then what to do, if else, what to do, and what is the middle ground. So here I'm getting a variable and I'm saying, okay, if this variable is larger than 0, then print something like that. Otherwise, if it's smaller than 0, print this. And if none of these were true, then, so that's the else one, then print this one. And then we have our for and while loops. They allow us write instructions to be repeated over and over as many times as we decide for. And then within these kinds of loop operations, we can decide to continue based on some control structure, or to break out of the loop, stop the loop, basically, again, based on some conditions. So here is an example. So I have a list of students and I want to create apparently a dictionary of student IDs. So here I'm creating a loop structure. I'm saying for each student, and that's just the name I gave to this variable. It could have been for S in a student or anything. So it means it's gonna go iteratively over the elements of the list. It's going to take each element out and then do something about it. So for each student in the list of students, I'm getting some input apparently here from the user. So I'm saying, hey, user, enter the ID for this particular student. Or if they want to quit, so if they want to break out of the loop, they press Q. If they want to not enter any ID for this particular student, they can just say continue. So if they pressed C, I will just go to the next student. I won't come here anymore. So the effect of break or continue is that I won't continue afterwards. If it's continue, I will go to the next iteration of the loop. If it's break, I will come out of the loop actually. So if none of these two happened, then what happens is that now I can assign, create a key for that student and then assign an ID to it. Now here afterwards my work is done whenever I'm out of the for loop, either because I just finished going through all the elements of the list or somebody as the user pressed Q and I broke out of the loop. Now I'm here and I'm now going through the keys within this new dictionary that I generated, and I'm going to print the IDs of the students. So that's another for loop or an iteration structure that I created. So when we are programming, there are usually a lot of things that we would need to do over and over for several times, not necessarily within a loop, but sometime in the beginning of my code I'm doing that, and then sometime else I might be doing exactly the same thing, but applying, I don't know, some distance calculation, for example, between two coordinates. I might need to do this many times for different points. So these sets of instructions, specifically if they are more than one or two lines, I don't want to just copy paste those instructions again and again and again over my code. Instead, I'm going to embed those instructions into what we call a function and then call that function into whenever I need it. So a function has always a body. It means the instructions that that function has to implement for us. It has an identifier, so we always call it something. We give a name to it. It has Probably it's not obligatory, but it can have parameters. Parameters are the inputs to that function. And then again, possibly it has some returns from it. So whatever that function has to return for us to take out. But sometimes it's not returning anything. It's either doing an in-place change to its input parameter, or it's maybe just printing something. So it doesn't necessarily always explicitly do a return, but sometimes it does. So I asked actually a couple of different AI agents with different prompts to see how best they could create a short lesson on Python. And it seems to me that this prompt works quite fine. And most of the AI agents, whether ChatGPT or Gemini, or Claude or others, they would succeed to give you a good workflow or framework to learn Python. So if you're new to Python and you want to initiate yourself on Python with the help of an AI agent like Copilot, ChatGPT, or Gemini, or whatever else that you have access to, then this sounds like a good prompt to give them. So ask them to teach you Python, but in certain ways so that you can easily follow those. All right, so I will stop sharing my screen so that I can bring up the first exercise or the first practice that we will have on machine learning. And if you want, you can use this time to take a quick break of 5 minutes as well. So we will gather back at 12:45. All right, we are back. Can somebody just confirm that my screen is still visible and this time we see some kind of browser?
Yes, Jupyter tab.
Yes, perfect. Thank you. All right. So I just want to say that for this, if I have to code, because I'm sharing now a different screen to be larger for me to be able to write on and see correctly, um, you you might see my face just turning from my camera. Uh, I apologize for that ahead of time. I'm gonna just make this a little bit larger so visibility is better here. All right, so if you're in the Google Classroom, um, under module number 2, I posted a little bit of welcome note. So here I just tell you that we will be able to directly run everything together with me through the Google Colab, which is some kind of Python, or actually it's programming, not just Python, um, environment that Google provides with backend from Google. It means everything processing power is Google's and not your local machine. Everything is pre-installed, so you don't need to take care of installing anything. You just open the Google Colab notebook and we can run directly from there. But if you're interested in running things afterwards, after this session, and testing or use them for further developments, the practice is to create a Python environment dedicated to that task that you're doing. The reason is that sometimes for different kind of projects, basically, you might need different types of packages. And these packages may also have different versions, and certain projects may need certain packages with certain versions, and then another project needs different types of packages or the same packages but with different types of versions. So you want to isolate sort of the environment in which you're running your Python programs for any particular project. So usually you would either containerize that as in a Docker concept, or a simpler way to do that is to create Python environments. There are different ways to create Python environments, and one of the easiest ones is through Anaconda. So Anaconda is sort of helps you containerize your Python environments, basically. We call them Conda environments. So here I posted some instructions on how you can do that. You need to download the software Anaconda first and get it installed, and it works whether on Linux, Mac, or Windows. And once you have that, you would be able to create your environment. Now, whenever you create an environment, you have to give it a name. So here I'm calling the environment, for example, tutorial, and you have to say what version of the Python should be installed within this environment as the base or the default type of Python environment setup. So for these exercises, to make sure that we have exactly the same environment as the Google Colab provides us, we go with Python version 3.12, which is one of the most recent versions of Python. Um, and that once you run this kind of command, it will start creating the environment for you. So it will actually be a physical folder on your machine that is called tutorial within under the directory where Anaconda is operating in your machine. And it will be this environment will exist now to work from. So you would go and what we say is activate that environment. It means we tell our Conda which environment we want to work on now. So you might have 10 different projects running, each of them having different needs in terms of the environment. So you might have 10 different environments on your machine. You will try usually to, because these also take a space, and you want to avoid duplications as much as possible, but sometimes you don't have a choice but keeping projects environment independent from one another so that they won't contaminate each other with wrong versions of the packages and stuff like that. So we'll go activate that, and we will see that it's activated. Then I have created for you a requirement file. I've placed it on our GitHub repo. The requirement file is basically a list of the packages and their versions that we would need to be able to run this whole project. Any of the net notebooks of this project that we have would collectively need these kinds of packages, and the versions I've specified them so that we make sure we all have a consistent and unique type of environment to work from. So using that requirement file, we're going to install all the packages from that requirement file into our environment. Now we have an environment that is ready to be used for implementing or running our Python programs. So any of the notebooks that we are going through, you can run it directly from that environment. So you would go activate your environment and just say, you would just make sure that you're on the path to your notebook and then activate a Jupyter notebook call or a command. And once you have this command, it will open a Jupyter environment for you, or a Jupyter lab it's called for you, through your browser, where you can navigate to your folders where the data and the notebooks are located, and from here on you will be able to run your notebooks. So this is for people who want to try this on their own at home, or just for future implementations. Now you know that a project needs to have an environment, and whatever packages you need for that project to run, they have to be installed in your environment. So that makes your project sort of contained in terms of running requirements. All right, so let's go back to the classwork. So we saw this item together. Next would be this one first, our first tutorial. So again, the same notebook, you will find it here under tutorial 1 or on GitHub under tutorial 1 again. Advantage of accessing the Google Classroom is that you can directly run it in Google Colab. But again, using Google Colab requires you to have a Google account. So let's go through this first tutorial together. So first things, I'm just going to connect myself to a new runtime. It means a runtime is sort of like a contained backend where your code will be sent to and will be running from there. So I'm just going to first connect myself, making sure that I can run something. So it's just telling me, okay, within this sort of virtual runtime that I gave you, you have about this much, this 12.67 gigabytes of RAM available and 107 gigabytes of disk. And this is what you can do. Now, for people who are following me along, I strongly suggest that you make a copy of this into your own Google Drives before you even connect or you start running. And to do that, you just have to say save a copy in Drive. When you do that, it's going to ask you for your permission to access your Google Drive. It really is a very light file. It's not going to take much space, so a normal Google account will definitely have enough space in your drive to save this. So save a copy and then work out of that copy, please.
Sorry, Majdi, I was trying to interrupt you. Is there another way of accessing this? Because the Google Classroom is full, and a lot of folks,
Oh,
yeah, we've
okay.
reached the maximum number of size, so
Yes, I
quite a few
can
folks.
directly send you the link. So just use your own Google account and open this link, basically. And as I said, make sure that as soon as you opened it, use the file menu and save a copy in your drive. So can somebody from outside the Google Classroom confirm that the link I sent here works for them? Perfect, thank you. Great. All right. So now we can tag along. So this first one is quite simple tutorial. If you remember in the first module, we said that when we do some classification or some segmentation, we would be able we should be able to evaluate the performance of our models, and there are various metrics to measure the performance of a machine learning model. When we are talking about just classification, we're talking about accuracy, precision recall F1 score, either overall ones or per class. And when we are talking about segmentation, we additionally have the intersection over union measure, which is a very good measure to understand how well we detected the outline of our object as well. So for any given class, to calculate these matrices, we first need to count the true positives, false positives, and false negatives. Um, Basically, true positive is that, let's say we are talking about class C, a certain class of uh, oak trees, for example. So when it's prediction and the ground truth are the same, so the ground truth of this item is telling me it's an oak tree, and I also predicted it as an oak tree. This is one item. This item adds one count to my true positives. And we have false positives. It means we wrongly predicted an item as class C. That becomes a false positive of class C. We have false negative. It means it was class C. It should have been class C, but we predicted it as something else. So that's one count for the false negatives of class C. And then we have true negatives. It wasn't class C, and we didn't classify it as class C either. And then we can calculate our per class matrices, precision recall F1 score, and per class accuracy, which is a little bit awkward sometimes. We usually skip the per class accuracy actually, and I will explain why. You will see that in the equation of the per class accuracy, we have true positive plus true negative divided by all the predictions. So true positives, true negatives, false positives, and false negatives of a certain class. Now, usually, true positive is uh, okay. So let's say I have 200 oak trees that are correctly identified as oak trees. 200 is my true positives. And true negatives is related to all of our other classes. So usually true negative, if the model is performing well, true negative is a very large number because everything else that we didn't identify as an oak is a true negative, right? So when true negative becomes a large number, then sort of our accuracy per class measure sort of inflates virtually. It doesn't have a very good meaning, basically. That's why we say usually the per class accuracy, if it's high, there is not much into it. If it's low, of course, something is wrong. But if it's high, it doesn't mean our model is necessarily a good one. We have to go and look at the precision and recall per class. But the overall accuracy is a nice measure because we can say we had this many items of all types of classes and we correctly identified this many of them. So it's a overall percentage of performance, and it's a nice one. So we're going to go through an example and we're going to calculate all of these for that example. And always when you're doing something for the first time, you're not sure about even what you have to expect out of these functions that you're writing. A good practice is to give yourself a sort of a dummy example, a very simple one that even on paper you can calculate what you need to expect as output from the function. And that way you make sure that your function is returning the right things. It's working properly. It doesn't have bugs. You didn't code anything wrong. And once you're sure, then you can apply that function on a real example, on a real input. So always come up with, we call this sometimes unit tests for those functions. So when you write a new function, you're not sure if it's doing the right job or not. Give a very simple input to that function where you do know what the expected output from the function should be so that you can evaluate it. And this is exactly what we're going to do in this first tutorial. So in a tutorial, in a Python program, as we saw, we always need some packages, and those packages should be imported. So here are the list of the packages I'm going to use within this tutorial. NumPy is a package for working with matrices, with arrays. So anything matrix to matrix multiplication, holding data into an array like an image, for example, can be brought into the memory of your computer program as a NumPy array, for example. Matplotlib is for doing some plots and figures. Peel is a library, it's called Pilo actually, for reading images, for example, from our machine or from internet. And OS for operating system, whenever we want to work with something to define paths or access to data, we usually need this library. So any of these blue bonding boxes around a set of codes. We call them a cell in notebook terms. So we're gonna run our cells one by one, basically. So the first cell I'm running, it's gonna ask me a few things. It's gonna say that, hey, this notebook that you have, somebody had put it in GitHub. Uh, that somebody is me. And it's saying that just make sure that you're not passing any secret or anything, or that code is not harmful. You should be very careful when you get a code and execute it, because if that code has, for example, access to your Google Drive, it might alter some files or something. So always make sure that you trust the source of a code that you run, whether you run locally or you run it through Google Colab. So I'm going to say run anyway. I trust it. So the first thing it did for me, whenever I see a tick here, a check mark, it means it finished running this cell. So it finished importing all these libraries. Now I'm going to write my function. So as we said, a function has an identifier. So here's the name of my function, calculate precision recall, exactly what it actually has to do. And then it has input parameters. We have a label, which is a NumPy array of the actual labels that my image, each pixel of the image should have had. So my images are H by W in terms of size of the pixel, whatever that H or W could be. And predictions are the predicted classes for each pixel of my image. And again, the size is should be the same exactly as my labels. And then how many classes do I expect to see across this mask and this prediction? So am I doing binary classification? So I have only two classes. Do I have three classes? Whatever. I just make sure that I enter them here. And then what it's going to return for me are the per class precision recall F1 score. And because I have potentially more than one class, I'm going to return those as lists. So each item of the list or each element of the list will contain each element of the list will contain, for example, the precision of one of our classes. And then we have to calculate the per class accuracy and the overall accuracy. I didn't, and I left it to you as an exercise. So I think as our first exercise could be a fun thing to do together. So I'm going to explain how this is done. So again, because I'm returning for several precision recall if I want to score an accuracy for all of my classes, I define them as empty list to start with, and then I'm going to append the precision, for example, that I calculate for each class into this list. So what I'm going to do, I'm going to go through my classes and I'm going to calculate those counts, the true positives, false negative, and true negative. And the way, and it's very easy. Basically, first I have to find out when my prediction is the same as the class. So all the pixels that are predicted as class C, and I have to find the ground truths, so all the pixels that were supposed to be C. And then exactly following this logic, I'm gonna give instructions, but in machine language, to calculate the true positives, and false negatives. So it's basically true positive when both the prediction and the ground truth are saying C, right? So it means here I'm prediction C is true or false, and ground truth C is also true or false depending on whether that pixel represented class C or not. So if they are both false, it doesn't give me a true positive. If they are both true, so if this pixel was predicted as C and it was also a ground truth C, then it gives me a true positive. For false positives is when I it wasn't ground truth C, but I calculated as prediction C. So the ground truth C is 0, but I predicted it as C, it's 1. So 1 minus 1 should be 1. It means if this scenario happens, if this condition happens, it's a false positive. I have to count that in. For false negatives is when it was a C, so the ground truth is 1, but I didn't predict it as a C. So the prediction is 0. So 1 minus 0 should be 1. If this condition happens, it means it's a false negative. I have to accumulate it. Now, for those of you who made a copy of um, this notebook into your own Google Drive and you're running along with me, why don't you go ahead and write how we should calculate the true negatives. And it's interesting because the AI agent of the Google Colab is already giving me a hint how I should write it. So please go ahead and whatever you think is right for that, write it. So keep in mind, true negative means both the prediction and the ground truth should be 0. So if you need a cheat sheet on tutorial one from the GitHub, I do have the full notebook with the solution to the exercises as well. So this is how it should have been done. There are actually multiple ways, but this is correct. For example, when it means both of them should be zero, so definitely their difference, 0 minus 0 gives us 0. But be careful because 1 minus 1, the true positive, also gives us 0. So we can calculate this, but we have to make sure we remove the true positive count from it to get our true negative count. And now that we counted this, it's very straightforward to implement the calculation of precision and recall because we just exactly follow the same equations. We just implement the same equations as a Python code. You just may notice that I made sure that the denominator here is not zero. Because if it's zero, we have a division by zero that will return infinity. But in reality, if these two are both zero, we have to return zero for our precision, and same thing for our recall. And then again, for F1 score, it's exactly the repetition of the equation that we had here. So I'm just implementing that equation. And you notice that I'm doing this for each class. So I'm going to complete this whole thing for each class and then go to the next class. So you remember just this equation. All we have to do is to place this equation back to calculate the accuracy per class. I'm going to just copy paste. So I just did it a little bit fancier. The total number of my predictions, so all the trues and all the falses, should be actually equivalent to the size of my inputs. So the way I get the size of the input is through the shape function. Shape 0 is going to return the height, and shape 1 is going to return the width. So I just put an assert. It means check this, make sure this is true. If it's not, give me an error and come out of the program so that I know something went wrong. So sometimes these asserts are very helpful in your code to just pick up any possible mistakes that you might have in your inputs. And then exactly repeating this equation, true positives and true negatives divided by the sum of all of them. And now that I calculated pair items for this class, I'm just going to append it to my list that will be returned eventually. So now for accuracy, it's actually already saying what I have to do. It's saying the accuracy you calculated, you need to append it uh, to the class accuracy. Now, this is wrong what it suggested because what I need for overall accuracy is the total number of correct predictions to the total number of predictions. So total number of predictions is easy to calculate because it's the multiplication of height to the width of my prediction. But the total number of correct prediction is this TP, right? So I just have to accumulate the true positives over time. So I started by 0, so that every iteration of the loop, I add the true positives of that class to the total number of correct predictions. And then once I come out of the loop, now I can calculate my overall accuracy, which is whatever I have accumulated so far divided to the total number of pixels, which is the height multiplied to the weight of the to the width of the image. And then this return is saying, okay, we calculated all of those. Now let's just return them. So whoever calls this function later, they can exactly get access to all of this. So when I run, nothing particular would happen. It's just a definition of the class here. So all that will happen is that my program will now be aware of the existence of this function. And if there is any major syntax error, it's going to throw it out at this point. So it was successful. Now we can go to the next cell. Now this function is to define the IOU, to calculate the IOU. Again, I'm exactly following the equation. I'm not going to go through it with details, but it's same logic. Each class has its own IOU, so I'm going to create a list of the IOUs of the classes, calculate it, and return it. So same thing, I'm running it. Nothing happens because it's just the definition here. Now, I've defined this function so that it can assign nice colors to our ground truths. So let's say I have a binary semantic segmentation. It means my image goes in and each pixel of the image will be either 0 or 1. So 0, for example, being the background and 1 being my class of interest. Now, I could show it as a black and white, for example, or I could assign different colors to it. So I created this function so that the user can assign whatever fancy color they want to each of their classes. So it takes the mask, those 0, 1s, or if I have 3 classes, it's 0, 1, 2. And for each class code, so 0, for example, they provide me with a color. And I use that color to colorize their own mask. And then for visual printing of stuffs, I wrote this function that would calculate and show the matrices, takes an input image, the ground truth mask for that image, the ground truth or the annotated semantic segmentation mask for that image, the predicted semantic segmentation mask for that image, the number of classes. This is an item I won't go a lot through, but sometimes when in your image you don't have, let's say, one of my classes is class building, and I have an image that absolutely has no building in it, but then the fact that I didn't find any building in it is not much of a success, right? I shouldn't let that bias or inflate unreasonably my performance matrices. I should put my focus on images that actually had buildings and see how accurately and how correctly I identified those buildings, right? So that's if you not if you this thing that I added here is basically enforcing that if an image doesn't have a certain class, then don't count that image into calculating the performance metrics of that class for true positive case. Of course, if we wrongly detected buildings in it, then that's a failure. We have to point it out. But the fact that we don't find any class in any building in an image that didn't have any building is not a huge success, and we don't want that to inflate our performance out of proportion and be too proud of our model while it might not be that good actually. So that's very important fact. And so here, I'm just calling the function that I had already defined. This time with these inputs, it needed if you remember, it needs a label, a prediction, and a number of classes. Here my label is called annotation, my pred is called prediction, and then I have the number of classes. So I'm passing these inputs as the parameters of the function, and these are what the function returns. Those variables, I call them as PR for precision, R for recall, F1 for F score, AC for accuracy. These are the first four are per class, so it's a list. The length of the list is equal to the number of classes, and this last one is just the overall accuracy. So here I'm just printing, do a pretty printing of the of all the information that I got out of my function. So here we can go ahead now that our function is safely returning class accuracies and also overall accuracy. Now I can go ahead and print them here. So I do not need to exactly rewrite them. I can just change an existing part of the code. So accuracy per class is saved in this item. And I'm going to say also what is the overall accuracy. Overall accuracy is no longer a list. Um, it's just a number itself. So I'm just going to say print me the overall accuracy. I made a mistake here. So you see it already highlighted it even as I'm saying, as I'm typing, and it's saying this variable all underline ACC is not defined, and it's right because this one has only one C. So I've made a mistake here, fixing it. And then here I'm plotting them as a figure. I'm plotting the input image, the ground truth annotation, and the predicted mask. So when I see the metrics and I also see the plots, it will give me a clear idea of the performance. So again, here we only made definitions, so nothing specific happened. Now, if we've done everything correctly, this is how my dummy example should perform. So as I said, just to make sure that things are correctly calculated by my function, I define a very simple dummy example. I create a dummy image, I segment it to something that I decided with a certain number of classes, and then I come up with some prediction as if a model has predicted, but I enter those values so that I exactly know what to expect from my function. So let's run this one and see. And you see now here, I'm just calling that function above, the function that we defined here. I'm calling that function and I'm passing my image, my mask, my prediction. Here I have 4 classes, including the background, and I'm also defining what colors should they look like. So let's run it and see how it looks. All right, so it's saying that I made a little bit of note here so that my dummy example has some definition too. So this was the image. So somebody gave me this image, and then this is how it should have been segmented if my model worked 100% perfectly. This, whatever it is here, should have been identified as class green. This should have been identified as class blue, and this should have been identified as class yellow, and every other pixel should have been classified as background. So this is the ground truth, this is the annotation, this is the expected output from my model. But then I ran the model on this image, and it gave me something like this. It made quite a lot of mistake over this class. It means definitely has poor performance over the class green. And we can also see it here that my class green has the lowest numbers for IOU for, oh, sorry, that's class blue. This is here because evidently I didn't do anything correct for class green. So intersection over union for class green should be 0, and that's right. And precision is also 0. Recall is also 0 because I didn't identify anything related to class green correctly. And then for class blue, it seems like whenever it's blue, I almost correctly identify it as blue, but seems like blue is meddling in the middle of all the other classes as well. Something I can conclude from here is that maybe when I was training my model, this class blue had too many items, and sort of my model is biased towards class blue. So it obviously does a good job for class blue itself, but it also has affected other classes, and items from or pixels from other classes are now being classified as blue as well. And when this happens, it means that the precision is low. Precision, if you remember, it depends on false positives. Things that are falsely identified as class blue are just large. And if we look at this, we can see that our precision is quite low for class blue, but recall is high because when it's class blue, for most part of it, I identified it as blue. And then for yellow, it seems that both precision and recall should be good because for most pixels, I correctly identify them as yellow. And for other classes, only a little bit of this was identified as yellow. And we can see here that both my precision and recall are high for class blue. And then the first one is background. Usually we don't care about the metrics on background. Again, it's not a measure of success if we identify background as background usually. It's really those specialized classes that matter. All right, so now let's do this for a real example. I've put an image, a ground truth mask of that image, which shows burn scars and an actual prediction from an AI model that I had trained. Uh, so I've put all of them on Google Drive, so they are accessible through these links. Now, if we do the exercise together, what we will get as output using just the function that we had is going to show us our image. And then I had only 2 classes for this case because it's a binary classification, background versus burn scar. This is the ground truth. This is what the model should have done. And then this is the output from the model. So we can see it's not bad. It had made some mistake here. Maybe some of the edges are too rough. We didn't get all the details of the burn scar. So let's calculate and see how much of mistake we've done and how, in terms of actual metrics, how our model is performing over this particular instance. Again, image, ground truth, prediction, all on Google Drive. So what we have to do is to read these images, because basically these are all images too. This is the actual image. This is a raster in form of a mask, ground truth mask, and this is another raster or image in form of a prediction mask. So first we have to read them into the memory of our program. To do that, there are many different ways. In module number 3, we will see the ways of reading actual geospatial rasters. But for now, let's treat these as just images. It could have been a JPEG image or PNG image or anything. Let's just use a generic Python image reader to read this into our memory. I will use Pilo library. So from Pilo library, this is the right syntax to read in or to open an image file if it was on my local machine, for example. Now that I've put them on the internet, it's somewhere on a through a URL link. I want to access it. So I have to first make a request to get access to the URL link and then pass the content that I receive after my request, open it now as an image. So exactly what's happening here. I already pre-coded this part of the function for you. So what I want you to do, if you haven't worked with Pillow library or even haven't done Python programming, writing the rest of this might be hard to do from scratch, but I want you to try and prompt it through any kind of AI agent. You can just, if you start chatting with Gemini or with your Copilot or ChatGPT, any kind of AI agent you have. Again, if you don't know Python programming, if you know, go ahead and try your best with coding from scratch. But otherwise, let's see, or even if on your Google Colab, you can actually start. Uh, Okay, I don't have access to code generation here, but you can even ask from the uh, you can toggle to Gemini and ask directly from your Google Colab how you should code this. So the goal is to read in the image, the annotation mask, the prediction mask, and then call our function exactly how we did here, call our calculation metrics function on it so that we can get something like this as output. So if everything works, you should get something like this as output. And if you lost patience and you just want to try it, the cheat sheet is available on GitHub. So that also gives me a possibility to take a little pause. Let's be back in a few minutes. All right. I don't know if anyone tried it on their own, but for me, let's just go get the solution from here. All right. So what I'm doing here is I'm reading in each of those image files as a first as a pillow array, and then I make sure they are NumPy arrays because my function expected to see things as a NumPy array. So I read the image, I read the annotation mask, and I read the prediction mask, and then I pass those as inputs to my function. That function, again, if we hover over the function, it will show us the definition. So that function expected image, annotation, and prediction, exactly what I'm passing. Here, next item it needs is the number of classes. I know it's a binary classification, 0, 1, so I only have 2. And I keep this as true. And then here, next thing is the class color dictionary. So I'm saying for class 0, for the background, show it with RGB, with the green value. And for the foreground, for the burn scar, which is class 1, show it with red color. So let's see what happens. So it took a little bit of more time this time to run, 4 seconds, because it had to load images that are online somewhere on someone's Google Drive to its own runtime processor memory, and then here next it will go through showing us, so passing through our function. So it did calculate, again, class 0 is background. We don't care much about but the class 1 is our burn scar. For this particular image, again, it doesn't mean my model is going to perform the same on every image, but at least for this particular image, I can see that I have a very high IOU because the extent was pretty much the same as the ground truth extent. I have lower precision than recall, and it makes sense because there are places that I shouldn't have, like if you see this area, for example, I shouldn't have classified them as burn scar, but I wrongly had done it. So precision has dropped. But whenever it was burn scar, I correctly identified it as burn scar, so recall is high. So that's for our first one. Again, if you just ran, if you made the copy on your Google Drive, if you want to save the changes that you've made so far to your Google Colab notebook, just make sure that for you, a save will be, for me, save won't do anything right now because I directly ran it on my GitHub and I'm not going to push this thing to the GitHub. But for you, the save will make a will update the copy that you created on your Google Drive. So that's for our first one. Maybe just thumbs up if some of you succeeded to follow along through the Google Colab with me. Great. So a few people succeeded to do that. I'm glad. And for those who didn't face an issue or just didn't want to prefer to just listen to me, if you later decided to try it, you can again do it directly through Google Colab or through your machine with the instructions I provided. And each of these material on the Google Classroom, they have a place for you to add comments. So ask your questions, please, as comments, and I will answer them as soon as I see them. All right, so going back to classroom, now we are on tutorial 2. This is our longest tutorial for the day. I won't explain too much into the Python programming side of things anymore. I will focus on what was the purpose of that piece of program in terms of our work related to machine learning. So this is um, this is a tutorial I prepared based on a data set from Germany. They have released, so in Germany, they maintain plots of forest where they do collect terrestrial data, like the height of the tree, the crown diameter, the diameter at birth, at burst height for the trees. And then on top of this information from terrestrial observation, they had added satellite observations. So for each tree, for each sample of a tree, they had observed the Sentinel-2 imagery multispectral band values over time, multiple times for each tree, and they released this as a data set. So I've put the links to the paper that explained that data set, the availability of the data set itself as well. I'm not going to run this particular notebook. The reason is that it depends on a large database file that is provided through this link. So if we go here, we accept that we are getting out of Google Colab. So the file that I've worked with is this file. It's a compressed SQLite database. So it's you can see several gigabytes when it's compressed, and when you decompress it, it's become, I think, 7 or 8 gigabytes of a file. I haven't uploaded it anywhere. It's anyways already on the internet. So that's why I'm not going to run this live with you. Uh, I will just go through the example. So this here is a little bit of explanation about what this data is. It's a database. So for each item, uh, which is a tree sample, we have all of this information. We have a unique ID assigned to that tree. We know from which plot uh, forestry plot and which corner of the plot that tree comes from. We have some observations for that, so we know the time of the observation. We know what kind of tree that is, so the species. We have the bottom of atmosphere reflectance values for that tree that are observed through Sentinel-2 imagery. We have a quality mask calculated for those observations of Sentinel-2. So we would have known if it's coming from a cloud or shadow or snow ice. That would help us later to filter our observations and make sure we're only using the good observation, satellite observations. On their side, they had already decided which sample should be used as a training sample or as a test. I'm going to ignore this and build my own data set. And then some other metrics and characteristics like as I said, the diameter at breast height, the crown area of the tree, the geographic coordinates, so latitude, longitude, and latitude of the tree where those observations were coming from, and some other information here. So now, again, I need a bunch of libraries to run this to run this notebook. So they are all from, again, math library, SQLite 3 for reading my database, daytime to be able to work with this feature here, which is the time and is expressed in Linux time. So I want to be able to work around that. Uh, Everything is going to be into matrices, into arrays, so I need to have NumPy to work with them. Pandas is a library that allows me to communicate with data frames. I will explain what a data frame is. And Polars is another version of Pandas that allows to work with data frames that are huge and large, which is the case of this data set actually. Matplotlib, like before, for plotting stuff. So Scalearn or scikit-learn is a library to do there are a lot of machine learning related functions available through this library. GeoPandas is very much like pandas, but for working with geographic data. So first thing I have to do is this data set again was provided by the data creators as a SQLite database. And what I have to do is to read in that database and start working with it. So the first thing I'm doing here is simply loading that database into my not the whole database, but a connection to that database for my program. So this database itself is huge. If you want to load this database into your memory, you would need something like 30 gigabytes of RAM to do that. For the sake of this, so usually you don't do that. You just filter the parts of the data set that you need and you load that into that part into your memory. So for the sake of this exercise, what I'm interested in is classifying my trees and identifying three specific types of trees. They are spruce, beech and pine, and from the description that the data creators had provided me, I know that those three types of trees are identified by IDs 10, 100, and 20. So what I'm doing here, I'm saying that I don't need the whole database to be loaded. These are the columns I'm interested in, and also filter those data points into trees that are either uh, beech and spruce and pine. Make sure this is a tag that according to the creator of the data, it means the data was re-observed. Is corrected, it means somebody has actually manually made sure this is corrected. So I want the best part of this data set to be taken. And then is pure, it means if the observation they made, they are sure it's from the tables, from the tree. So a couple of quick filters here to narrow down the number of samples from the database that I want to load into my memory. And I want to load it into a data frame. So a data frame is a sort of a series of data or a container sort of for numerical data that has attributes, numerical data with attributes in Python. So when this part of code is exactly doing that. So here I also print the shape of that data frame. So you can see that right now, even after this filter, I loaded into my memory about almost 10 million samples. And there are 10 columns, which is exactly the number of the columns I'm reading in. And then with this command, I'm looking at the 10 first items in my data frame. So this is just an index, but here I can see the species. The species is identified by an integer 10, which is actually a type Bruce. And here is the bottom of atmosphere spectral values. This is a code that shows the quality. This is the dBH in millimeter, height in decimeters, crown area in meters. The time as a Unix seconds, we will convert this to something that we can understand better. Each tree has a unique ID, and if you note that all of these 10 items, they come from the same tree, it means, but the dates are different. It means we observed the same tree many, many times. And of course, because it's the same tree, the coordinates of the tree didn't move. So these show where the whereabouts of the tree. So now I want to do a little bit further cleanup in this. First of all, this representation of the spectral values in binary format doesn't work for me. I want it to be changed into actual integers, signed integers that I can understand better, and make sure that they are represented as a list of 10 items, each of them being the reflectance from one of these bands. So these are the order of the bands there. So this is the first thing I do. I make that conversion from that binary format to actual integers. So now if I look at my reflectances, these are values I can understand as a human. Next thing is about this time. I have no sense of what that means. It's just the Unix second time. So I would convert that time into a human readable time. So for example, this huge value here, it means time zero at 5th of August 2015. So a little bit of cleanup at the first level. Then I'm going to go actually doing some filtering on my data. Whenever you want to do machine learning, you've definitely heard of garbage in, garbage out. You don't give bad data to your model and expect good results, right? You don't train your model on poor data. If there are ways to clean up your data, to filter your data, and to keep the best samples out of your data, or at least have a clear understanding of how good and bad your data set is, then that's a winning scenario for your model. So that's exactly what I'm going to do here. The creators had already, when they were calculating the reflectance values for the tree, they also assigned a quality value to that so that we would know whether there were shadows or clouds or high atmosphere particles involved. So I'm going to use that and do some filtering. The second thing is that it seems like the times are all over the place. I have data from spring to winter. So maybe to make things a little bit more uniform and depending on my need, I may need to also filter the time. For example, if I'm developing this machine learning tree classification model to do my forest inventory on an annual basis, maybe I can just collect my data every summer and run this model on a seasonal basis. Every summer, I update my forest inventory of the country. So that means I don't need to use the data that come from winter or fall or sometime else into training my machine learning model because I know that in the future I will never give it winter data. I will always give it only summer data, right? So these are things that I can do to clean up my data. So exactly for that, I'm gonna start by cleaning the time. I'm gonna keep June, July, and August data only, so summer data only, because in the future, I have the plan to update my inventory, forest inventory only during summers. This model will only see summer data. I wrote this function a little bit more globally. I do know this data comes from Germany, so we are in the northern hemisphere, and summer is represented by months 6, 7, 8, June, July, August. But in case the data was from southern hemisphere, then summer was represented by other months, or depending your use case. Like I was just this morning working on some data from Dakar, and I made sure that data come from dry season because anyways during the wet season there's so much clouds and everything that my data quality will be low. So for whatever work I want to do it during that season. So that's how you decide to filter the time of your observations. So after this, I already reduced the size of my data set to about 3 million. It means a more concise, a more concentrated and focused data set already. So the second thing is about that quality that the creator has assigned. So those they are in terms of binary again representations, but they mean either that data is valid, either there was no data, there is cloud, there is snow, water, and everything else. So I want to make sure that only things that are really clean, doesn't have any cloud, doesn't have any high atmospheric particles, the illumination condition is not poor, there's no snow, I already filtered my data to summer, so the chance of having snow ice is really low, but still I want to make sure there is no snow ice and all of that. So the next filter that I apply here, and I will jump into here, is that I make sure that all the no data, all the clouds, snow, water, it could happen if it's been really rainy, and then my pixel, instead of representing the actual tree, is representing water rather. Most of the pixel is filled with water rather than the tree leaves, for example. If the particles are high, if the illumination is bad, if the sun was at a lower elevation, if there's a saturation happen, all of these, it means shady data. So I want to avoid those data points. So I will go and remove all of those data points. Now, there was a question whether we remove duplicate positions. It means because we said that for each tree we have multiple observations. I would say that this is some test I want to do later to see whether it's okay to keep only one observation per tree, or is it better to have multiple observations for each tree? Because that actually multiple observation, it means redundancy and probably some more information about my tree. So that this is I want to I don't want to remove it right away. I want to keep that and during my experiments, my machine learning experiments, decide whether I want all the observations for each tree or only like the median or mean of the observations for each tree. So that's something we'll actually look at later. So after cleaning by the quality itself, I'm already reduced to 2.6 million data samples. And then because I don't need this quality anymore, I just needed to do my cleanup. I don't want to tag it along as part of my data. It's huge values, large volume of contribute to a larger volume of data. So I'm just going to drop that data out. That column out. The other thing is that reflectance values normally shouldn't be negative, but they can be negative if there has been some outlier involved. So I make sure next filter that I'm applying is dropping all the samples who have at least one negative reflectance value in all of their 10 bands. So that's when I'm gonna drop that as well. So it was 2.65. Now I have 2.64 million points. Um, then another feature, and I might not use it later, but it seems like relevant because we were talking about vegetation, trees. So maybe some kind of a vegetation, spectral vegetation index, like a normalized difference vegetation index, could be a useful feature to have for my machine learning purposes. Again, not sure whether I will end up using it, but to do experiments, it seems like a relevant feature to have. So what I'm going to do is go ahead and calculate it. It's based on red and near infrared bands. I'm going to calculate that and add it now to my as another column to my data frame. So we can see that in the new look of the data frame, I don't see anymore the quality one, but I added the NDVI one. So because I already did a cleanup on my reflectance values, normally the NDVI should be between -1 and 1. But just to do as an extra sanity check, I'm going to make sure that NDVIs that are not eligible values are filtered out, which apparently I didn't have any because I'm exactly at the same number of features as before. And now I'm going to do some train and test splitting. So usually you would say, okay, I have 100 samples. Randomly, I would keep 20% of those samples for testing and 80% for training. And then within that training data set, I will keep a percentage again for validation, and the rest would be training. Or if I want to do k-fold, as we spoke about, then I will divide that training data set to, let's say, 5 pieces. And during my experimentation, I will choose one of those pieces as, or one of those portions as my validation. But here, it's a little bit more complicated than that because each individual tree had more than one sample in our data set. And we don't want to accidentally do a leakage of training data into our testing data. If I do just a random, let's say 30% of the data set be test and 70% be trained, then it's possible that the same tree showed both in my train and in my test, and it's sort of cheating here. We want to avoid that kind of situation. We want to make sure that our train and test are truly splitted. There is no tree overlap between them. The second thing, this is geospatial data. These trees, they do have coordinates. I know where the trees come from. And of course, trees that are much closer to each other, they have the tendency of having the same species, right? So it's sort of cheating as well if I get one tree in train and then the tree that is just beside it into test. Of course, the model, if it learned this one, it's going to learn if it's going to predict this one correctly too, because they were anyways too close to each other. They very probably are the same. The model didn't necessarily do any effort. It's what it is, right? So that's why it's very important that I do a wiser or more intelligent type of splitting between my train and test data set. To do that, I'm going to say, first of all, let's find, find the subgroups within my data set of unique trees. And I did have that tree ID column in my data set to be able to do that. So that's the first thing I'm going to do. I'm going to group them. Second, I'm going to group them by closeness of the coordinates. So I'm going to divide my country. So here, the country of the data, Germany. I'm going to divide Germany into a coordinate grid, and then I'm going to make sure that one grid, trees from one grid, only contribute to either train or test and not both of them. So this way, I'm I'm adding a security check of not leakage of geographic information between the train and test data set. So this is exactly what I wrote here, this function to do it. And I'm going to be honest with you, I provide the instructions to an AI agent to help me code that much faster than if I had to start it from scratch. And of course, I corrected that, made sure there are no bugs, and it exactly does what I intended it to do. But that's exactly how I did it. So I grouped my data by tree ID first, and I made sure because each tree ID anyways had only one coordinate, that's what I'm aggregating those coordinates as well. Once grouping, then I converted those coordinates from degrees to meters so that my grid can have, for me, working with meter distances is a whole lot easier than working with degree-based distances. So I converted those coordinates to X and Y in meters so that I can say my block or my cell sizes in the geographic grading I want to do should be, for example, 20 kilometer. But this is something I decided right now. I could have changed it and see its impact on the machine learning uh, process as well. So this is something that I could have test. I should actually test with it and see which one is better. I'm doing a 30-70 split for my train and test, and then the train itself is being split again to 80-20% for validation and train. And that's how I find which samples in my data set should be trained, which ones are which one validation, which one are test. And then I save that thing as a, and I do a few sanity checks. I make sure that there is no overlap of tree IDs between train and test and train and validation. There is no geographic overlap between train and test and train and validation. You can see overlaps are 0. That means I did a good job of splitting my data. Now in my train data set, I have about 30,000 samples or unique. I have about 30,000 unique trees, but these many samples because each tree was observed more than once. I have these many unique trees in my validation and these many unique trees in my test data set. So afterwards, I'm going to write it out into an actual file system. Uh, this new curate, we call it a curated and also a splitted data set that I created now for training purposes. Now I'm gonna save that out to a file so that in the future I don't need to repeat all of these things to get my data back. I have a data set cleaned and saved somewhere. The format of saving a data frame is depending on you. If the data set is small, you can save it as a CSV file. So each row of the CSV file will be one sample and each column will be one feature. But this data set is still huge. It has 2.4 something million samples in it. For writing it to a CSV file, it would have taken like 350 megabytes on disk. It's a huge CSV file. And I chose another format. It's called Parquet. Parquet is an open source Apache format, column-oriented binary file to store data frames. So I just dump my data frame into this Parquet file that I can use later. And here, actually, I'm going to use it right away. I'm going to read it back in. This time, I use that Polar's library to read my Parquet file. And the advantage of Polars compared to Pandas is that it's not going to actually load everything into memory. Instead, it's going to keep it into what we call a lazy memory and then stream from it as we need. This is a very common and modern way of handling large data sets using Python, like large duty files, large data frames. We don't we don't read them all into memory at once. We keep them in a lazy virtual memory that can be as large as we want, and then we just bring or collect back parts of the data that we do need to work on through streaming from that lazy memory. So Polars is a library that allows us to do this thing for tabular data. So what I'm going to do here, those reflectance values, if you remember, they are sitting in a list under one feature. But in reality, each of these is actually a feature. Like this is blue, this is red, this is green, and so on, right? So I want to just move them out of a compact list and bring each of them into its own column so that later working with them will be easier. So this cell is exactly doing that. It's just parsing my Parquet data and is replacing and is converting that list of bottom of atmosphere reflectances into columns that I named them with the actual name of the spectral band, and then I drop that list altogether. I don't need it anymore. So and then I just resave uh, my Parquet file, this time with the corrected names for reflectance values. So now that I have my Parquet file, my data file set up for me, now I can go and start doing the machine learning process. So that would be, we can move into our second uh, notebook under tutorial 2, the exploratory data analysis. So whenever this is, sometimes the data is produced by yourself, you already have a very good idea of what this data represents, how the features are related, what each feature means, how each feature impacts the class of your samples and so on. But most of the time you actually don't know that. So that's when you have to do this kind of explorations on your data sets to be able to understand your data better. So that this part of the tutorial is exactly for that purpose. So again, I'm bringing in some libraries that I want to work with. That Parquet file, I've already uploaded it on Google Drive, so we can directly read it in from Google Drive. We don't need um, to have it locally. Of course, if you want to run locally, you can do that as well. Whenever if you're running these things along with me, let me connect. Again, first, if you want to run, make sure that you made a copy on your own Google Drive. So go to File, save a copy in Drive, and then start running. So the first thing would be importing my packages. Again, it's warning me, hey, you didn't create this. Uh, this is coming from a GitHub. You didn't create this notebook. Be careful about what you're running. That's the first thing it told us. It might take a little bit longer to load everything because now I have more libraries and larger packages being called in. So I will let that happen on its own. And then the second part is just reading my data in, again, in a lazy format using polars. And I'm just going to take a quick look at its columns or attributes, making sure that everything I had. Oh, yes. Let me also copy the link here. I copied the link also into the chat. So I'm going to make sure that everything is in good shape. All of the columns that we just saw in the previous notebook, they are still in our data set. All good. I also see their formats. I want to just make it a little bit more visually pleasable. We we know that ID 10 in the tree species column is referring to spruce, and ID 20 is referring to pine type of tree, and 100 to beech. So it's just the I'm creating a map between the IDs of the classes and the actual names of the classes. And then here I want to just get an idea of how many samples and how many unique trees of each species do I have in my data set. That will give me a very good idea whether my data set is properly balanced or it's an imbalanced data set. So that's what I'm printing here. I'm seeing that for I species 10, which was spruce, I have about 16K trees, unique trees, and these many samples, again, because each tree is observed more than once. That's why the number of samples is much larger than the number of trees. And then for 20 is the pine. For pine tree, I have this many trees, and then for beech, I have this many. So we can see quite a large imbalance. This is an imbalanced data set we are working with. It means we have almost 2 times more pines in this data set than spruces, and we have almost 3 times more spruces than beaches in this data set. That means our data set is imbalanced. So that's something we have to keep in mind when we are going to go ahead and design our machine learning model and the learning process itself. So that's the first thing, that's the first insight I got about this data. Now, the next thing, I'm going to decide which columns or which attributes of this data set should be used as features for training my machine learning classifier model. So for now, I'm going to keep everything, basically, all the spectral bands, all the structure related features, geographic features, even the time of the observation, and the additional vegetation index. And of course, one way to do experiments through machine learning process is to change the configurations of these selected features and see their impacts on our model. But for now, for observatory purposes or exploratory purposes, let's suppose I want to train a classifier on this data set using all of these features. So what I'm going to do here is for visualization and exploration purposes, I want to do it at tree level and not at sample level. So I'm going to first reduce or regroup my data frame by tree, by individual trees instead of individual samples of trees, so that I can, instead of working with this large data set, I can work with a smaller data set. And in terms of meaningfulness, it's just as meaningful. I just don't need to do plots and observations on huge data sets. So that's what I did here. That reduced into a total of 51,000 individual trees here. So visualizing data distributions and class separability. That's something you usually want to do. You want to see these three classes, are they as a human? Can I really distinguish them if somebody showed me these features of one type of or one class of tree and features of another tree? Can I tell the difference actually? Because if there is absolutely no separability between the classes, then maybe the machine learning model will also have a hard time. So to do that, I'm going to do some plotting. Let's first of all see geographically how these trees are distributed. So I'm using a I'm using a package called Shapely to do a plot of the geographic distribution. You can see the shape is pretty much the shape of Germany. So the data comes from all over Germany. I've shown each type of tree by a different color, and the size of the circles, I've adjusted them based on the crown diameter. So that gives us a little bit of um, more realistic perception of the trees. So we can see that there is some geographic grouping already. It seems like most of the pines of Germany happen to grow in the north, and most of the spruce happens to grow in the south, and then beech is pretty much everywhere. So we started by noticing some geographic separability between our samples. Next, again, in the sense of understanding the data imbalance, I plot the number of samples per type of tree. So here a visual proof that our data set is imbalanced, highly imbalanced. We have a whole lot less samples, for example, from this class. We call it a minority class or a rare class because it doesn't have as many samples. And this is a majority class or a high frequency class because it has a lot of samples in our data set. Then here I'm plotting a number of samples per tree, number of the observations that each unique tree has. So I can see here that most of the trees have between 20 to 80 observations or to 90 observations. And it makes sense if you remember we reduced to summertime. Summertime we have depending on how many passes of Sentinel-2 we had and how many pixels represented each of our trees, that's how we might have had multiple observations, how we got multiple observations for each tree. And that's how it's distributed. So a lot of our trees have actually around 60 observations per tree. Some of them have less, some of them have more. Then here I'm plotting features distributions. So for example, I'm plotting the NDVI. I can see that the distribution is looking quite different for each. They do have overlaps, so they are not as separable, but at least their means, they seem to be uh, quite far apart. That gives me some hope that these three species are separable indeed. They can be classified, for example, using NDVI. And if I look into uh, diameter or height, a little bit less. We can see that these distributions get closer and closer and more similar to each other. That means maybe these features are, or here you can see for crown, um, pines and spruces, they almost have the same distribution. It means if crown area was my only feature to classify my trees, then there was no way that I could distinguish a pine tree from a spruce tree. There's a little bit of chance I could get the beech trees, but not this one. So it seems like actually the structure features might not have that much of relevance at the end, at least for this three specific types of tree. And here I'm just plotting some of the reflectances, like bands, like here near infrared. Again, some separability, yes, not. Ooh. Here with the coordinates, we did notice that our pines, they do have a tendency to be at higher latitudes, and that's what we see also here. For spruces, we had a bit of concentration in the center and a little bit of concentration in the south, and that's what we see here. And then beaches, we saw that they were pretty much all over the map. That's what we see also here. All right, so now I want to find if these features have high correlation just by looking at their values, not related to the relation of the features to the classes, but just between their values. So I can calculate the correlation like this is just a numerical correlation again. And I can see that, for example, my NDVI is highly correlated with near infrared, which is a normal thing because to calculate NDVI, I did use near infrared. And that should be a sign for me that between the near infrared band and NDVI feature, I don't need to use both of them. I could, because I'm using both red and near infrared, then maybe I could just drop NDVI. It's anyways seems to be highly correlated with that. So these are the types of insights we can get from a correlation map. Now, next thing is what we call feature scaling or data harmonization. If you notice, if we go back to a preview of our data set here, we can see that the range of these values of our features are quite different. Like blue values, we have 200-ish, green values, 400-ish. I don't know, crown diameter is some range, height is a different range. So we cannot input these values as they are into a machine learning model because the model is going to think about these values and say, oh, if something is large like that, it's like 1,600, then maybe this is more important for me to pay attention to that than something that is zero point 0.6. But this is absolutely not the case. This magnitude of of the features has nothing to do with their relative importance in training of my machine learning model. So I have to first bring all of these values into a similar range. They don't need to be exactly in the same range, but into a similar range, harmonize it so that my model wouldn't pay uh, extra false attention to any feature just because its values are 1,000 times more or 1,000 times larger than the values of another feature. So that's exactly what I'm doing here. I did write you a little bit about different ways that we can do this kind of scaling. We can go through our training data samples and find the minimum and maximum of these values and then use that to bring everything between 0 and 1 or between -1 and 1. If we see some kind of normal distributions as we, for example, noticed here for coordinates, for example, I do not see any normal distribution. So doing a Z scoring or using the mean and standard deviation of coordinates to normalize these features is a wrong thing to do. But for some of these other ones, they are almost having a normal distribution. So it does make sense for me, or a Gaussian distribution, and it does make sense for me to normalize this data in order to change their scale. So that's what I'm going to do here. So for each of my for each of the features, I decide how to normalize. And then this UMAP is we already saw it in action during the how is it called? The module number 1 theoretical part that is used to reduce the feature space so that maybe for us as humans, it will be easier to make an interpretation of our data. So as part of my exploration analysis, what I'm going to do, I had all of those features from 10 reflectances and 3 structure types, coordinates, time, everything. I'm going to put them into a UMAP model and ask it to reduce it to 2 features. Again, I don't know physically what those 2 features mean, but maybe they will give me a better understanding of separability of my classes within this new reduced feature space. And that's exactly what I'm doing. So what I see here is the result of that. So this axis and this axis, they are representing feature number 1 and feature number 2. I have, again, physically speaking, no idea what they mean. But we can see it's interesting because we can see now some separability in our data, but also some confusions. We can see that beeches and pines, they can be distinguished, but it seems like I should expect my eventual machine learning model to make some confusions between between spruces and pines, for example. So this is the type of idea it gives, uh, type of insight that you can take from this. This was for train samples, and I did the same for test. And like the same model that was found on train, I applied it to the test, and I can see that the distribution is still very similar to my test train. That's a good news. Usually, your test data should not be out of distribution compared to your train data. And the fact that they look similar within that new feature space, it's it's a very good news. It means my test data is now out of distribution. But this still has this, probably I'm going to face this problem eventually. And that the pine trees won't be easy to distinguish from some of the spruce trees. So when I'm doing my machine learning design, I have to make sure that I come up with a strategy to deal with these potential confusions. First of all, I have to pay attention to it in my metrics, and I have to make sure that I deal with it somehow. So that becomes a machine learning strategy for later. And then another aspect of exploration analysis is feature importance. How important each of these features will play a role in detectability of any of these classes. So how important a feature is. Is it like I included all of the attributes of this table as feature, but was it really necessary? Do they really contribute to an eventual classification model? And there are again lots of ways to calculate feature importance. I've listed them here and I've implemented 2 of them. One of them is using a base classifier like a random forest classifier, and the other one is using a library called SHAP, or Shapely Additive Explanations. And the result looks like this. So this is the level of importance, and these are my features. So you remember we actually saw it too, that they don't, like the structure, the crown height and diameter, they don't seem to contribute, they don't seem to represent separability of our classes. And again, we observe exactly the same thing here, that they don't seem to have a large importance. Same thing for the day of year where the observation was taken. Maybe because I already reduced my data to summer, so which day of summer this comes from doesn't seem to have a lot of impact. And then this is the second way of calculating importance, where it does it per class. So it's a little bit more detailed insight about the importance of features that we can get. And pretty much same conclusions, that like these 4 are always somehow end up at the bottom lines, a little bit less maybe for beach with the crown, because we saw that the crowns are larger generally for a beach. But they still end up at the bottom. They are not at a high level of importance either. So that gives me some ideas how I should engineer my features. Which features should I pick up for training a good classifier model? Which features seem to be useless? And so I shouldn't waste my processing time on including those features in the model. They might even just cause more confusions than anything else. So all of this exploratory analysis helps us design a better foundation model. Like we saw, for example, our data is imbalanced, so we have to make sure we do something about it when we are designing our machine learning model. So I list an exercise here for you to do at home later if you're interested. Now, the last one is doing the actual job of the classification. So again, same thing. If you want to run, please make sure you made a copy on your drive. So I'm starting to design my classifier now. So I'm going to just point out to where the Parquet file is. For a quick test, I also have a different tree into a CSV file. I have to identify where I want my model to be saved. And if you're running this from Google Colab, comment these lines from here and uncomment these lines, all of this, so that the run will take place on your Google Drive. Because Google Colab does not have access to your local machines. The only place they can save data to is your Google Drive. So you have to make sure you comment these lines and you uncomment these lines to run this notebook directly from Google Colab. So that's what I've already told you about feature scaling and the different strategies of scaling that are used for different types of features based on the visualizations we had in the last notebook. So for that, I wrote actually a class. A class is a higher level type of embedding instructions in a cleaner way and a more modular way of embedding information in Python. So I wrote a class whose main job would be scaling my data set. And then I'm later you will see that once this class is initiated, I am going to save that the object. When you initiate a class as a variable, we call it an object. I'm going to save that object for future use because the way this scalar is working is looking at the trained data set and find out the ranges or the means and standard deviations that we have to have for the scaling process. So I want to, in the future, when, for example, I'm doing inference from my model, I want to be independent of the trained data. So I need to make sure this scalar is stored somewhere and is accessible for future reference. So for the sake of this tutorial, I'm saving this as a joblib file. So it will be a .joblib file either on your local machine or on your Google Drive if you're running from Google Colab directly. So what I would say is that be very careful. So if you did not create the joblib file yourself, be very careful about loading a joblib file into the memory of your on Google Colab. It's less important because it's something on a virtual machine basically. But if you're doing this on your own machines, do not load any joblib file that you might find because it might contain harmful code or harmful data that will hurt you. So just a notice that there are various formats of data for various formats of files for storing data of a Python program. And all of them can be actually harmful if you don't trust the source. don't use it. So now, when we are working with a I'm going to use actually PyTorch is a package in Python that is very powerful for writing, for developing machine learning and deep learning models. So within PyTorch, whenever you want to interact with your data set, you use a PyTorch data loader. So a data loader will basically go through your data set and make it ready to input it into the model. So you always have to make sure that your data set is defined in a way that PyTorch data loaders can understand them and interact with them. For example, your data set should always have a function get item because that data loader is going to go through your data set, get an item out of it, pass it to the model. So you have to, there is some architecture to respect when you're designing your data set. That's exactly what I did here. This data set is gonna go through my pandas data frame, convert the features that I want to work with. So here I want to work with all the features uh, again as one experiment with my reflectance features, structure features, so those height and stuff, vegetation, the NDVI, the time and everything. And I want to make sure that all of those features are available to the model. So I gather those features from my data frame. I make a NumPy array out of it, and then the data loader of PyTorch can come and take all of those features with it to go and input it into the model. And then for each of my samples, of course, I have to know the type. I represented it with Y. It's just the value between 0 to 2, 0 for spruce, 1 for pine, and 2 for beech trees. So I just made a conversion so that, again, I don't need to work with 10, 20, and 100. I work with the smaller numbers, even for representing my classes. So this is how the PyTorch dataset is defined. Now, if you remember, we did see that our dataset is pretty much imbalanced. It means if I don't do anything about it, when I'm training the model is going to see many more examples of pine tree than beech trees. So that means the model is going to become biased towards pine tree. It's going to end up classifying most things as pine. For example, it's going to misclassify all of my beech trees. So to avoid that, I'm going to come up with a sampling strategy. So if you remember from module 1, we said that we cannot put all of our data into the model at once anyways, because it's just the limitation in the memory. So we would batch our data, patch our data into smaller batches, let's say 4 samples at a time. These 4 samples go to the model, do the feed forward and the back propagation. The next 4 samples go in and so forth. Normally, if your data is balanced, this is how you would do it. Simply divide your training data set into batches and pass those batches one after another into your model. But now that our data is imbalanced, we're going to make sure that we create more batches, more repetitive batches of our minority classes compared to the majority class, so that our model sort of ends up seeing the same number of samples from each class in each epoch of the training. So this is called a weighted sampling strategy. So I do not change the data set itself. I do not create copies of the data set. All of this will be handled through a weighted sampler that PyTorch provides to me. The only thing I need to do is to assign a weight to each of my classes. The smaller the weight, the less frequently that class will be sampled, the larger the weight, the more frequently it will be sampled. So my minority classes should always get a higher weight, and my majority classes should always get a lower weight so that it balances out when we are doing the sampling. And this is exactly what I did in this part of the code. And here now I'm finally defining a deep neural network classifier model. So I'm defining it as a fully connected, so a multi-layer perceptron model. I'm saying the first one, the first layers are just linear layers, so what we do, just hidden layers basically. The number of neurons in the very first layer, the first layer is actually my input layer, so the number of features is not something I can play with. But my second layer, I wanted to have 128 neurons. Once I come out of this, I apply some activation. We talked about it in the first module as well. So this is how you code it. It sounded like something complex, but I'm just saying once you got the output of these 128 neurons, pass the results through a ReLU function to add nonlinearity. Then this batch normalization is to make sure that I don't have values from neurons that are hugely large. And then dropout is a mechanism to avoid overfitting. It's saying, okay, out of this 128 neurons, just randomly shut down 10% of them and move on. So, and in every iteration, this 10% will be a different 10% on a random basis. And it makes sure that we are not overflowing our neurons with information, and that avoids the risk of or reduces the risk of overfitting. And then I add another hidden layer, this time with 64 neurons in it, another layer, this time with 32 neurons, and my last layer should have only 3 neurons in it because I have 3 classes. So I need 3 scores coming out of this neural network model. So that's how I define my model, and I define a couple of functions here to pass data through the model, calculate the metrics, exactly same mechanisms that we saw in our first tutorial. When I'm doing training, I want to be able to save the model, so the weights and parameters of the model as an actual file to be saved. And once I'm done training, I want to be able to load, whether within this notebook or in another program, I want to be able to load those trained weights and start doing inference with them. That's why I need save and load functions for my model. These are those evaluation functions. We already talked about all of these metrics, precision, recall, F1, and so. And then the training process. The training process is exactly as we saw it in module number 1. We have our batches of data. We pass that data. So here I'm going through, we do this first of all iteratively, so through several epochs. And in each epoch, I will go get my data from my data loader, a batch of data. So this is one batch of data out of my whole data set. I will pass that data through the model. So this part is doing the feed forwarding. Then calculate the loss. Then I'm going to back propagate through the loss to improve, using the optimizer to improve the weights of the model, then get some metrics about the performance of the model up to this batch of data and this epoch, and then repeat that over and over as many times as it's needed to be able to complete the training and make sure the model is has learned what it has to do. So here, I won't run it, but I did finish the training. I set only 5 epochs, and it seemed to be actually flattened already as 6 epochs. And something I did was also, and I don't know if we can, I will show you my TensorBoard. TensorBoard is a tool that I use to track and log the situation of training a model. So all of this information about each epoch, I can track them and save them as a tracked experiment. So I will open my own TensorBoard here for you to see from that, from when I had run this. Just a second. Mhm. So the command is running the TensorBoard with logdir and pointing it to where your runs are being saved. And it would create for you, oops, something happened here. Localhost. So this is my TensorBoard. This is the run I had, and I can track during the 5 epochs of the training. I can track how the accuracy, all the other scores, the loss function, how are all of this have been changing. So I can see that the loss on training was reducing, but it seems like I might have actually overfit this model because the loss on validation has started to grow after just 2 epochs. So these are all parts of our machine learning experiment. We have to play around with all of these parameters around training the model are hyperparameters basically to make sure we are able to not overfit or to train just for the right amount of right amount of epochs to get that. So after that, once the training is finished, I can do all of my evaluations. We talked about confusion metrics. This is the confusion metrics I get from my first attempt in training this model. The results are actually not bad at all. We can see that expectedly beach we did have problem with it because it's a very small data set for beech trees. So our F1 score is a slower is a smaller on that one, and exactly that the precision is low for beech trees. And we can see that in terms of confusions, we do confuse spruce and pine with each other as we expected because that's we saw also in the UMAP model that this is going to be something that happens, and we have to find a better way maybe in our model to deal with that. And here I'm just showing the distribution of the test data over Germany, so we can see where most of the mistakes has happened. The red ones are where I didn't classify the tree correctly, and green is when it happened. But the good thing is that I did keep all the samples. I trained on samples instead of individual trees. So if I group the predictions on samples and just take the average of the predictions for the samples, then we can see that I'm doing a much better job per individual tree. That means redundancy of information basically is in my favor this time. Each tree having multiple observation helps at the end to aggregate the results of predictions per tree and have a better result. So now if we look at our distribution on the map, we can see a whole lot less red spots or incorrect detections. And just for the fun, I wanted to also show you the train samples. The black ones are train data set or train samples. You can quite see that they do have geographic separation from our test data. And the green one is correctly identified test, and the red is wrongly identified test. So we can see that actually that tree aggregation helped us. We did keep all the information, and at the end, once the model was trained, we aggregated the information over each tree, and it played in our favor. So I created an exercise for you to go through later. Uh, that would be concluding this module. You will notice that there is a third tutorial in module number 2, which is more about images and CNN. Um, I didn't want to go through it because module number 2 was supposed to stay on tabular and non-image data, but I just wanted to give you a very easy to follow example of how convolutional neural networks are defined, because they are mainly defined for structured data like images or point clouds and stuff. And I just wanted to put the basically theoretical training we had about convolutional neural networks into a code base so that you would know how a CNN is defined using code. But we're going to see a whole lot of this when it comes to our third tutorial. So I ask that you follow this tutorial. It has very detailed explanations again. You can again run it directly from Google Colab or run it at home. So please go through it. Just it's a complimentary tutorial for module number 2, even though we were not supposed to do image data in module number 2. So I hope this was helpful to you guys, and thank you again for being with us today. And I really hope to see everyone back in our module number 3 on 22nd of April, where we will go through next level, get things a little bit more sophisticated, start working with actual geospatial rasters, geotiffs basically, do some more complicated tasks like change detection using foundation models, as well as semantic segmentation using CNNs and transformer types of models. So I hope to see you back in module number 3, where together with one of my colleagues, Victor, we will be presenting that session to you. Thank you again. I did notice that our Google Classroom has capped in terms of number of participants. I'm very sorry for those who didn't get a chance to join the Google Classroom, but all the material from Google Classroom are also being posted on GitHub. I'm just going to make sure these Google Colab links are also added to our GitHub for those who had to copy them from the chat here, so that later you won't lose access to those links. Thank you so much again, and wish you happy afternoon or evening, or depending on your time zone, what time it is. See you next time.